Assalamu alaikum, dear student. Today is the lecture number 3 of week number 4. We are continuing the chapter number 2, pressure and fluid statics. In today's lecture, the topics we are going to cover today are buoyancy, flotation and stability. Under this heading, there is a topic remaining, which is stability of a fluid floating body. And the last topic of this chapter is the fluid in a rigid body motion. And under this heading we are going to study rigid body translation motion and rigid body rotation. So let's talk about the stability of a floating body. So in the stability of a floating body, we are also going to discuss an important concept of a metacenter. So we will see what exactly it is. So under the heading of stability of a floating body, for floating bodies the stability problem is more complicated, since as the body rotates, the location of the center of buoyancy which passes through the centroid of the displaced volume may change. Okay, so here is the difference between the stability of a floating body and the submerged body. Okay, so in case of the submerged body, the center of buoyancy do not change, it remain constant regardless its body is moving within the water, but the center of buoyancy never change. But in the case of floating body, the center of buoyancy may change. As it is saying here, you can see in the previous article it has been mentioned that for submerged body, for the state of equilibrium, the center of gravity of the body must be below the centroid or center of buoyancy. This not applicable for the case of floating body. Okay, so there is another thing we see in the case of submerged body. Okay, for the stability, the center of the body will be stable in the case of submerged body when the center of gravity is below the center of buoyancy. But this is not the case in the only case in the floating body. Under certain conditions, the floating bodies remain in equilibrium even when the center of gravity lies above the center of buoyancy. So one case is fixed: if the center of gravity lies below the center of buoyancy, whether the body is floating or submerged, the body will be stable. Okay, but in the case of floating body, under the certain condition, the floating bodies remain in equilibrium even when the center of gravity lies above the center of buoyancy. Okay, this happens because in such cases the center of buoyancy B relative to the body shifts as the body is given some angular displacement, and the shift in B is enough to provide a restoring or equilibrium moment. Whenever a body floating in a liquid is given a small angular displacement, it start oscillating about some point. The imaginary point about which the body oscillates is called metacenter. Okay, so here there is a concept of metacenter. The metacenter may also be defined as the point where the line of action of the force of buoyancy will meet the normal axis, okay, centroidal axis of the body, when the body is given a small angular displacement. So here you can see in the picture the concept of metacenter and metacentric height is more clear. So here is the centroidal axis, okay, or the normal axis or the symmetrical axis. Okay, so here you can see, so this is the symmetrical axis, normal axis or centroidal axis. So here you can see the basic floating position is calculated from equilibrium. The body's center of mass G, here is the center of mass G and this is the equilibrium position, and from here we can calculate the other positions. Okay, so this is the equilibrium position and this is the mass G. This is the center of gravity where the mass is acting, and the weight is acting downward, which is W. This is the center of mass, and the center of buoyancy are computed, and this is the center of buoyancy when the body is in equilibrium position, and the center of buoyancy and the center of gravity lies in a same axis. And here you can see the center of buoyancy is below the center of gravity. Here you can see the center of buoyancy is below the center of gravity. The body is tilted a small angle. In the second case, here you can see we tilt a body, we give a small deflection to the left. We give a small deflection to the left, okay, to a floating body. So what happens? And a new water line is established, and there is a new water line. This is a new water line is established, okay, but the center of gravity is still on the same line, okay, but the center of gravity is still on the same line. So here you can see a new water line is established for the body to float in this angle. The new position B of the center of buoyancy is calculated, and the center of buoyancy is shifted from this center line to this new position B dash, okay. The center of gravity doesn't leave its axis, but the center of buoyancy leaves its axis, and it's moved from this line to this new position B dash. A vertical line drawn upward from B, a vertical line draw upward from B dash, okay, we draw upward line B dash, and it intersects the symmetrical axis at point M, called the metacenter. So this point where the new position of center of buoyancy or the buoyancy axis intersects the centroidal axis, that point is called metacentric point, okay, and called the metacenter, which is independent of the small deflection. Doesn't matter how small or big is the deflection, okay. So now the point 3, in that case the metacenter is above G. If point M is above G, you see, if the point M is above G, that is if the metacentric height mg is positive, this is mg, okay. If mg is positive when m is above g, so what will happen? A restoring movement is present and the original position is stable. So here you can see there is a restoring movement. This is the center of buoyancy, there is a line of action of center of buoyancy, and this is the center of gravity. If you take the movement, okay, somewhere point here, so what will happen? You will see there is a restoring movement against the deflection we given at the beginning, okay. So this restoring movement will make this body stable, okay. If m is below G, if metacenter point m is below G, what will happen? The mg is considered negative, the metacentric height is considered negative mg. The body is unstable and will overturn if disturbed. Stability, okay. So if we disturb in this case, when the metacentric is below G, if we disturb, what will happen? There is a overturning movement. The body will not be stable. If it will give an overturning movement and body will sink. So here you can see G and M is giving, if you take the movement across this point, what will happen? There is a movement which is supporting the initial disturbance. So that means this movement will sink the body, or it will make the body unstable, okay. So here we can see the stability increases with increase in G. If mg is positive, the body will be stable. If mg is negative, the body will be unstable. More mg will be more. If mg is more big, the body will be more stable. So let's see how now we can see what are the conditions of stability of a floating body. So here you can see some practical application. A floating body is stable if the body is bottom heavy and thus the center of gravity is below G below the centroid B. Okay, so that we know in both the cases, if the center of gravity G is below B, both in submerged and in the floating cases, the body will be stable. Okay, or if the matter center M is above G, however, or this is another case, okay, even the center of gravity is below B but M is above G, the body will be stable in that case also. Okay, yani M is above G but B is below G. You see, the B is below G, okay, but M is above G. So this is another concept. In the case of floating body, the body will be stable. However, the body is unstable if M is below G. Okay, now here we can see the condition of stability of a floating body. So when the center of buoyancy is above the center of gravity of the floating body, the body is always stable. Okay, under all condition of disturbance, a right couple is always created to bring the body back to the stable condition. Okay, second, when the center of buoyancy coincides with the center of gravity, the two forces act at the same point. A disturbance does not create any couple, and so the body just remain in the disturbed position. There is no tendency to tilt further to correct to the tilt. Okay, so this is the case one what we have discussed earlier. When the center of buoyancy is below the center of gravity, as in the case of ship, additional analysis is required to establish whether the body is stable or unstable. Okay, so this is only in the case of floating body. So let's see, this involves the concept of metacenter and metacentric height. When the body is disturbed, the center of gravity still remain on the centroidal line of the body. The shape of the displaced volume changes and the center of buoyancy moves from its previous location. The location M at which the line of action of buoyancy force meet the centroidal axis of the body. This we can see already in the previous picture, but we will see in the further analysis. When disturbed is defined as the metacenter. The distance of this point from the centroid of the body is called the metacentric height. Okay, so let's see and analyze how we can calculate the metacenter and metacentric height. So let's see in this example, stability of a floating body continued. From this figure shows a body floating in an equilibrium condition. This is the first case. The body is in equilibrium condition when the center line where both center of buoyancy, the buoyancy force and the weight of the object acting in a same line. Here it can say the weight acts through the center of gravity G and the buoyancy force Fb acts through the center of buoyancy B of the displaced fluid in the same straight line as W. When the body is displaced through an angle theta, the case B, if we displace this object little bit, okay, towards the right, okay, if I give a small deflection towards this right, this is the disturbed displacement theta we give it to it. Okay, so W continues to act through G. The volume of the liquid remain unchanged. Okay, so here you can see the weight of the object is still acting at the center of the center line of the object. Okay, but the shape of the volume changes. But here you see the volume is remain same, but the shape of the volume is changed. So because of that, the buoyancy will, because of the location of the center of buoyancy will change. Here you see what is the shape of the displaced liquid. This is the shape of the displaced liquid, some kind of rectangle. Okay, but here you can see the shape of the displaced liquid is some kind of triangle. Okay, some kind of triangle. So in case of the rectangle, this was the center of buoyancy, but in case of the rectangle, we don't know exactly the position of the center of buoyancy, but the center of buoyancy shifted from point B, because this was the point B initially, so it shifted from B to B dash or B1. So here you can see that, but the shape of the volume changes and its center of gravity, which is the center of buoyancy, moves relative to the body from B to B1. So it moves from B to B1. Okay, since buoyancy force Fb and W are no longer in the same straight line. Now we can see the buoyancy force Fb and the W are no longer acting in the same line. They are acting in a different line. Okay, so because of that, what will happen? A turning moment proportional to this is Wx. Okay, so please make a change. This is Wx is produced. So this is W and this is X. So there is a returning moment, Wx will be produced, which is in the figure Fb. You can see this is force and this is X. This will give a returning moment. Okay, this will give a returning moment to balance the applied disturbance. Returning moment Fb and is a rightening moment and Fd is an overturning moment, and in the figure it is showing as a overturning moment. Okay, we give a disturbance in this direction, but this is given showing a overturning moment. Okay, the same concept. Okay, the same concept. So let's see how we can calculate this metacenter M and how we can calculate this X. So let's see, if M is the point at which the line of action of buoyancy force cuts the original vertical through the center of gravity of the G. So here you can see this is the we take a vertical line straight away up to the centroidal axis, so where the centroidal axis intersects the line of buoyancy, that point is called metacenter. Okay, and mg is called metacentric height. So let's see how we can calculate mg and how we can calculate x. So here you can see x is equals to gm into theta, or theta means theta, since it is very small, so actually it is gm sine theta. What is x? You can see from this angle, if this is x, okay, and this is theta. So this is what is this? This is sine theta, or it can be tangent theta. So this is gm to gm sine theta. So x will be equal to gm sine theta. So since theta is very small, so sine theta become the, so the point M is called metacenter and the distance gm is the metacentric height. Comparing figure B and D, it can seen that if M lies, okay, if you go to the figure B and D, here you see M is lying above G, here M is lying below G, that means between G and M, and here M is lying above G and M. Okay, so here we can say that now by comparing these two pictures, if M lies above G, a rightening moment W gm theta is produced, equilibrium is stable and gm is regarded as positive. Okay, so now the sec, if M lies below G, okay, an overturning moment W gm theta is produced, equilibrium is unstable and gm is regarded as negative. If M coincides with G, the body is in neutral equilibrium. Okay, so in that case, how we can find the metacentric height, which is gm, that is equal to gm is equal to bm minus bg. What is bm and what is bg? So bm we can find out by using this equation, moment of area along its centroidal axis into divided by submerged volume. Okay, if you know these two values, you can easily find out the Bm and minus Bg. What is Bm and what is Bg? You can see here that this is Bm, and what is Bg? Bg is given here. So if you minus this from here, you can easily calculate the metacentric height. So this is the end of the topic. I'm going to start the last topic of this chapter, the fluid in rigid body motion. So what we are going to study in this section? In this section we obtain relations for the variation of pressure in fluids moving like a solid body with or without acceleration in the absence of any shear stress. That is, no motion between fluid layer relative to each other. Okay. So many fluids such as milk and gasoline are transported in tankers. In an accelerating tanker, the fluid rushes to the back and some initial splashing occurs, but then a new free surface, usually non-horizontal, is formed. Each fluid particle assumes the same acceleration and the entire fluid moves like a rigid body. Okay, so no shear stress developed within the fluid body since there is no deformation and thus no change in shape. Rigid body motion of a fluid also occurs when the fluid is contained in a tank that rotates about an axis. So what is the condition of a rigid body? The condition of a rigid body is no shear stress is developed within the fluid body since there is no deformation and thus no change in shape. So this is the condition of a rigid body or a solid body. Okay, so we are going to drive an equation when the rigid body is moving with an acceleration. Consider a tank containing liquid moving with uniform acceleration. After initial sloshing, the liquid stabilizes and move as a solid mass. Okay, so here is the initial position of the liquid when there was no motion. When after back and forth, there is a final fluid layer we achieved. Okay, so the liquid distributes itself in the tank and slopes as shown in the figure. Since there is no relative motion of the liquid particle, the shear stress is 0. Consider a differential fluid element of side length dx, dy and dz. So this is a small element, okay, that we get after the acceleration. So and each side of the fluid element is dx, dy and dz in x, y and z direction. Let pressure P is the pressure at the center of the element. Consider the pressure P is acting at this point, P, X, Y and Z. Okay, this is the point. So that we have already discussed in the live session, how the pressure changes from one point to another point. Okay, if the pressure P is here, so what would be the pressure on this side after the dz, because this is at the center. From here, the distance from here to here is dz by 2 and the distance from here to here is dz by 2. Okay, so what would be the pressure at this surface and what would be the pressure at this surface? Okay, so from here, from the top, okay, so this is P Z, since it is going away from the axis, so P del in the Z direction, change in pressure in the Z direction, and what is this change? This change will come within the distance dz by 2. Okay, so this is the pressure multiplied by the area, dx and dy will give you the pressure force. And same at the bottom, since it is the magnitude, the scalar quantity which is closer, this surface is closer from this axis. If you take the distance from here to here, so definitely the pressure will reduce. So P minus change in pressure in Z direction and change in pressure due to the change in position from d by through distance multiplied by the area will give you the pressure for the bottom side. Okay, and there is a weight of the fluid acting in the z direction. Okay, and same all the forces in the x and y direction. Okay, so let's sigma force is equals to 0 in the z direction. So what are the forces acting in the z direction? P minus this force in the positive y direction, this is in positive y negative y direction, and this is weight acting in the negative z direction. Mass is equals to density into volume. What is the volume of the object? Dx, dy, dz is the volume of the small fluid element, rho is the density of the fluid element, and az is the acceleration in the z direction. So when we simplify this whole equation, it will become del p over del z, that is minus rho g plus az. Same if we sigma fx is equals to max and sigma fy is equals to may. So this will become finally, because there is no weight component in the z direction, so only it will be end up with del p over del x into minus rho ax, del p over del y into minus rho ay. Okay, so if the body is moving with uniform acceleration, the pressure will vary with respect to the uniform acceleration and the density of the fluid. Okay, so we see if the fluid is acting as a rigid body, there is no shear stress. Okay, so the condition of the fluid at rest must be fulfilled by this equation. Okay, so the special case 1, fluid at rest. What will happen in the case of fluid at rest? Only we drive an equation when the fluid at rest, it was P is equals to rho gh, or dP by dz is equals to rho into g. This we derived in the previous lecture. Okay, for the fluid at rest or moving on a straight path at a constant velocity, all components of acceleration are 0. Therefore, constant velocity means there is no change in acceleration. Okay, there is no change in velocity. The change in velocity is 0. That means all components of acceleration will be 0. A, y, z, all components will be 0. Okay, but so substitute the value of acceleration a0, z0 and y0. So only the component will remain, it is minus rho g. Okay, so in that case a change in pressure will be equal to minus rho g. So this is basically verified. Okay, so which confirms that in fluid at rest the pressure remains constant in any horizontal direction. P is independent of x and y and varies in the vertical direction as a result of gravity only. Okay, so P is the function of z only in the case of when the fluid is at rest, and this equation verifies that. Okay, so that means the fluid can act as a rigid body motion. These relations are applicable for both compressible and incompressible fluid. So we can apply if the fluid is compressible, so G will be acting as a variable. So here we are going to see that the fluid in a tank is moving in a particular direction. Okay, particular direction. It can be consider if there is a horizontal path, there is only acceleration along the one axis. Okay, but if the fluid is moving somewhere in a slope or in a ramp, so what will happen? There will be a two component of acceleration, ax or az. Consider y component is 0. Okay, so consider a container partially filled with the liquid. The container is moving on a straight path with a constant acceleration. Okay, the x and z component of the acceleration are ax and az. There is no movement in the y direction. Okay, here is y direction, and thus the acceleration in the direction is 0, ay is 0. The acceleration in the y direction is 0. Then the equation of motion for accelerating fluid becomes, so since the change in pressure is 0 because there is no acceleration, So change in there is acceleration in the x direction, so change in pressure will be del P over del X will be equal to this, and there is a change in acceleration in the z direction, so del P over del Z is equal to this. Okay, this we derived from the previous derivation in the previous slide. Okay, so here basically, as I told you at the beginning, here we are considering the case the fluid or tanker is moving in a ramp, so there is a two dimension. Okay, so therefore the pressure is independent of y. So here the pressure is the function of x and z. Okay, if it is moving in a straight path, so pressure will be function of only one component. But if the tank is moving in a slope, the pressure will be a function of two component, x and z, and it can be written in the form of partial derivative is like that. The change in pressure with respect to x due to the distance dx, change in pressure in the z direction due to the distance dz. Okay, so here we substitute the value of del P and del X, we put the values, and finally we simplified and we end up with this equation. So dz over dy is equals to a minus ax g plus az is equals to tan theta, which is equal to slope. So this is also called equation for the surface of a constant pressure or isobar. Okay, so this is basically a straight line equation. It's giving you a slope, and this slope is equal to this. By using this, you can calculate the deflection of the surface due to the acceleration, because once you know the acceleration, you can calculate the angle. Okay, rho is the constant. If you want to calculate the pressure between these 2 points, so where the density is constant, the differential pressure between 1 and 2 in the fluid is determined by integration to be like this. So just integrate this equation for the 2 points, the equation will become this. So if you are considering point 1 to be the origin, okay, where x is equal to 0 and z is equal to 0, where P is the pressure P naught, and point 2 be the any point on the fluid, the pressure distribution can be expressed as, okay. So this is your starting point where x and z is equal to 0, so you can calculate where the pressure is known. So this you can calculate by using this equation. So let's move on to the picture here. Here you can see this is your free surface, here the point 1 and point 2. Okay, so if you want to calculate the length between the point 1 and point 2, okay, so here you can see the vertical rise or slope of the free surface at point 2 relative to point 1 can be determined. Okay, so that means we can determine this theta by choosing point 1 and point 2 on the free surface. Okay, if I take both on the free surface, what will happen? The free surface, the pressure at point 1 and point 2 both are atmospheric pressure. So what will happen at this case? P1 and P2 will be the atmospheric pressure, and both R will be equal. Okay, and solving for Z2 and Z1, what will happen in that case? You can see if this one and this one will be equal to 0, so this equation will be reduced to del Z over Z2 minus Z1 will be equal to AX over GAZ X2 minus X1. So this is the equation can help us to find out the distance between 1 and 2. Solve a practical example. Overflow from a water tank during acceleration. An 80 centimeter high fish tank of cross section 2 meter by 0.6 meter that is initially filled with water is to be transported on the back of a truck. The truck accelerates from 0 to 90 km per hour in 10 seconds. If it is desired that no water spills during acceleration, determine the allowable initial water height in the tank. Would you recommend the tank to be aligned with the longer or shorter side parallel to the direction of motion? So we have a two side of the tank, 2 meter and other is 0.6 meter. So consider this is 2 meter and the other side is 0.6 meter, and height of the tank is initially 80 centimeter high. So when the tank transport with the acceleration, so what will happen after the back and forth, it will take a constant position of its surface. So this is the constant position of the surface, and since this is the initial level of the liquid, this is the center point. Okay, at this point there is no rise, there is no fall. Okay, this is at the center, and from center it is making an angle theta. Okay, and the rise is del zs. This is the fluid height. After that it will spill out. So we have to find out the height of the fluid after acceleration. Okay, so after that height, definitely the fluid will spill out. So let's calculate, and before calculation we should make some assumptions. Number one, the road is horizontal during acceleration, so that acceleration has no vertical component. Az is equals to a0. Effect of splashing, braking, driving over bumps and climbing hills as assumed to be secondary and are noticed and are not considered. The acceleration remains constant. So now what we analyze, we take the x-axis to be the direction of motion, the z to be the upward direction, vertical direction, and the origin to be the lower left corner of the tank. Okay, so origin is the lower left corner of the tank, so this is considered, this is the lower left corner. Okay, and this is considered the origin. Okay, so here noting that the truck goes from 0 to 90 km per hour in 10 seconds, the acceleration of truck is, so we can calculate the acceleration. A is equals to v over t, the change in acceleration in change in time. So time is 10 seconds, the change velocity from 0 to 90 km per hour. So we have to convert into SI system. 1 meter per second is equal to 3.6 km per hour. So after calculation we got the acceleration in the x direction is 2.5 meter per second square. Okay, so now to find out the theta, theta, we have an equation already that we derived. This is the equation. Okay, so we can calculate by we can calculate tan theta, because we know the acceleration. Ax is equals to 0, g is known, so we calculated the theta, which is equal to 14.3 degree, or the tangent theta value is 0.255. Now we can calculate the height for the two sides. Okay, because since we have two sides, one is longer side, one is a smaller side, so we can write down the maximum vertical rise of the free surface occurs at the back of the tank, and the vertical mid plane experience no rise or drop during acceleration. Okay, so as I said here, there is no rise or fall. This is the point, the midpoint. Okay, and this is the maximum rise. So here by the vertical rise at the back of the tank relative to the mid plane for the two possible orientation becomes the case 1. We are considering the longer side is parallel to the direction of motion, and this will be equal to b1 by 2. Okay, tan theta is equals to 2 meter by 2 into tan theta is equal to this. This equation is the same equation. Okay, this is the same equation. Del s is equals to this, tan theta you calculated, and x2 minus x1 is known. Okay, so because this is the point, here is x1 is equals to 0, this is your x2 that is known to you. Okay, okay, because here from here to here we have, from here to here we have 6, divide by 2 is 6 by 2. So this is, okay, b1 by 2 into multiplied by this, we calculate 25.5 centimeter. Case 2, the shorter side parallel to the direction of motion, that is equal to 7.6 centimeter. Here you can see this is the higher rise, this is the lower rise. Okay, if you take this side as a direction of motion, what will happen? The water will spill out from this side because the rise is very small. So that's why if you take this side as a direction of motion, the rise is only 7.6 meter that this rise can handle, okay, that this side can handle, but this rise cannot handle by the shorter side. So that's why, therefore, assuming tipping is not a problem, the tank should definitely be oriented such that its short side is parallel to the direction of motion. Okay, this is the shorter side. Emptying the tank such that its free surface level drop just 7.6 centimeter in this tank, in this case, will be adequate to avoid spilling during acceleration. So the last topic of this chapter is rigid body rotation, that I will explain during the live session of the course. So this is the end of the today's lecture.